For section 4.1, please download this handout, follow along, fill out the examples. When you are finished, this will serve as the quiz that you need to turn in. So scan your filled in handout and turn it into Blackboard. Let's take a look. Section 4.1. The first definition is let C be a number in the domain of a function named f. Then, f of some value c is the absolute maximum value of f on some domain if f of c is bigger or equal to the rest of the function for all of x in the domain. If it's bigger, then it's the maximum. The absolute minimum value of f on some domain if f of c is less than or equal to all of the rest of the function for all the x in that domain. If it's smaller, we call it a minimum. Let's look at an example or two. The max and min values are called the extreme values of the function. Here's my first example. F of x equals x squared. Let's look at a picture. This is f of x equals x squared. F of c, where c is equal to 0, gives me this point 0, 0. And at this point c input, the output is 0, and you can see f of x equals x squared. That point is the absolute minimum of f of x equals x squared. Let's take a look at a different example. F of x equals x cubed times 1 minus x. When we take a look at this function, we can see that the value c that makes their maximum point is this 0.76. And that is the biggest point, or the maximum point, for the rest of the function. Definition number 2. The number f of c is a local maximum value of f if f of c is bigger or equal to f of x when x is near c. Or we call it a local minimum value of f if f of c is less than or equal to f of x when x is near c. Near c means some open interval c. Let's look at a couple of examples. First, f of x equals cosine of x. When I look at a picture of cosine of x, this is a local maximum. There's a local maximum. This is a local minimum. This is a local maximum. The next example, f of x equals x cubed. Well, when I look at the function f of x equals x cubed, I don't see any absolute max or absolute minimum, and even the situation of a local maximum or local minimum is hard to see at first. But if I restrict this f of x equals x cubed to be on some, let's say from negative x is equal to -1 to +1, well, now I have a local max and a local min. This would be a local min, and this would be a local max. But the only reason it's a local min or a local max is because of how I've restricted the domain C. Next, let's look at the extreme value theorem. The extreme value theorem says if a function f is continuous on a closed interval from a to b, that interval is closed, then f obtains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d inside that interval. Notice that the extreme value theorem has two conditions. Condition number 1, the function has to be continuous. Let's take a look at a picture. This is a function that is not continuous. The black part of this function and the red part of this function are disjoint. So in this particular picture, the extreme value theorem does not apply. Condition number 2. It needs to be a closed interval on a to b. Let's take a look at another picture. This is the function e to the x. The interval for e to the x is negative infinity to positive infinity. That is an open interval. However, if we restrict the interval to be from negative 2.5 to positive 1, now the extreme value theorem applies. Number 4, Fermat's theorem. If the function f has a local maximum or minimum at some input c, and if the derivative of that function evaluated at that input c exists, then the derivative evaluated at that point c must equal 0. Fermat's theorem has two conditions. Condition number 1, the function has a local min or max. Condition number 2, the derivative of the function evaluated at c must exist. Look at this example. F of x equals the absolute value of x has an absolute minimum at x is equal to 0, but the derivative evaluated at 0 doesn't exist. So therefore, we could not use Fermat's theorem. Also be careful. In addition, the converse of Fermat's theorem is not true, which would be if the derivative of f evaluated at c equals 0, then the derivative at c exists or has a local min or max at c. That statement is not true. For example, look at f of x equals x cubed. Well, the derivative is equal to 3x squared. And if I evaluate that at 0, I get 0. However, f of 0 equals 0 cubed, which is 0, 0, and no local max or min exists there. Let's take a look at a picture. This is x cubed. And at the point 0, 0, that is neither a local max or local min. But as we demonstrated, if I take the derivative and evaluate it at 0, I certainly still would get 0. Number 6. The definition of a critical number of a function f is a number c in the domain of f such that either the derivative evaluated at c equals 0 or the derivative evaluated at c does not exist. Number 7. If f has a local maximum or minimum at c, then c is a critical number of f. Let's look at an example. Find the absolute max and min values of f of x equals x cubed minus 3x squared plus 1 on the interval of minus 1/2 to 4. First, let's take a look of a picture of this function. This is a picture of x cubed minus 3x squared plus 1 from the interval of minus 1/2 to 4. Number 1. It's important that we understand that f is continuous on negative 1/2 to 4. F is a continuous function on negative 1/2 to 4. Number 2 is we can find the critical numbers of f on the open interval minus 1/2 to 4. The first thing I do is take the derivative of f of x. When I take its derivative, I get 3x squared minus 6x. Then I set the derivative equal to 0. So 0 equals 3x squared minus 3x. I factored out the x, so that means x is equal to 0 or x is equal to 2. Now I need to plug these two values that I found, the critical points, into my original function. When I plug in 0 into my original function, I get f of 0 equals 1, which corresponds to the point 0, 1. When I plug 2 into my original function, I get f of 2 equals negative 3, which corresponds to the point 2, comma, negative 3. The next thing I need to do is find the endpoints of my function. Let's look at a picture. We found the critical points. The first one was 0, 1. The second was 2, comma, negative 3. But now we need to figure out what the value of each of these endpoints are. The first endpoint is when I plug in negative 1/2. I get 1/8. So that's the point negative 1/2, 1/8. Then I plug in the endpoint 4. So I get f of 4 is equal to 17. And that corresponds to the point 4, 17. Once again, these endpoints came from the domain restriction on the interval negative 1/2 to 4. So now I look at all of the points on my list. I find the one with the lowest value. 1, negative 3, 1/8, or 17. The point 2, comma, negative 3 has the lowest output value. So the absolute min is at the point 2, comma, negative 3. When I look at the picture, this is the absolute min. That's at the point 2, comma, negative 3. Then the absolute max, I look at all the output values and I find the largest value. In this case, that's at point 4, 17. So the absolute max is at the point 4, 17. And then finally, the final example. I would like for you to do that example on your own. Make sure you turn it into Blackboard. This will count as quiz number 9.